Well, welcome everyone to our April AGU Geodesy webinar. We're so glad that all of you were able to join us, and we're very pleased to have a talk today on geodesy and the next generation, interesting problems and needed skills. Our speaker today is a professor at the University of Texas at Austin, who has degrees in mechanical, aeronautical, and aerospace engineering. Also, a very distinguished record as through research in a variety of areas related to geodesy and space geodesy. Received many different awards throughout his career, especially last year from AGU. He received the Whitten Medal, which is given every 2 years for outstanding research on the form and dynamics of the Earth and other planets. So we are very welcome. Glad to have him here. We will have him give his presentation and close the chat and questions during the talk. And then when we are over, please feel free. I'll unmute everybody and open up the chat. So without further ado, please get started.
Thank you so much. And thank you so much for this opportunity to come and speak with the community. And the, the title was proposed in sort of a weak moment, shall we say. And the genesis of this title, and in fact, the theme of the presentation is that it is a time of change in geodesy. And it is a time of change forced by many things, some of which belong in the domain of geodesy, and some of those are outside the domain of geodesy, but we all have to react to that anyhow. And so me and my group, I was in the process of reinventing myself, and my group was beginning to do some new things. And so this had been on the top of my mind at about the same time that the white paper on the crisis in geodesy that has been much talked about in our community that came out. And so, uh, yeah, that's where this title came from. And then I realized that you give this title to six people, they're going to come up with six very valid and equally as good perspectives. So I shall have appropriate weasel words to make sure I don't claim to be the authoritative word on next generation interesting problems or the needed skills. All right. So myself, I started off at UT Austin as a PhD student in 1987 until about 2015. I was on the research track. 2010 to 2015, I was a research professor where I took on students of my own. And then 2015, I moved to the tenure track ranks and have been there. So basically, my entire professional career of 37 or so years has been at UT Austin. And my research portfolio, practically, I'll do anything to do with space flight and in service to space geodesy. So two parts to it, from physics today to Earth system science, how the technologies and experimentation and developments in physics can be used to serve Earth system science, particularly through exploration from space. And then a more recent interest in integrating lunar and terrestrial geodesy for obvious reasons. And that actually has one of the motivations for the reinvention, as I will talk about. So that's my background. Some cautions, still learning what tomorrow may bring. And this does not even refer to the events of the last 3 months when the science enterprise in the government is being reshaped. So this is actually even excluding that. So my anecdotes should not begin to sound like expertise. I still have a lot to do, a lot to learn. And specifically with respect to artificial intelligence, this was driven by curiosity. It was driven by fear of being left out. And trying to get it done as leavened by experience. And one of the stronger motivations there was to keep up with my students, every single one of whom appears to be an expert in machine learning. That's something I think the younger ones in the audience will definitely appreciate. The sample challenges are not an authoritative list. They are discussed as a prompt for conversation. So take a look at, I call it a challenge, and I take a look at the dimensions of the challenge. What part makes it challenging? Why did that challenge arise? And I think that will help us see later down the line in the next few years, sort of recognize challenges as they are coming up on us. I do have some biases and predispositions. All my geodesy is space geodesy. It's actually satellite geodesy in the sense that what you can do at the satellite. And then being an engineer, it is very strongly technology enabled. There is no new physics innovation that I did not like or did not think could be put in service to geodesy. Very much data driven. And so I don't have too many years under my belt in purely theoretical investigations. And my perspectives, they exclude a very important aspect of what you learn from doing experiments. So please keep these in mind. That's one of the reasons why the list of challenges and the opportunities they present is not exhaustive at all. All right, so what are the building blocks of our practice of geodesy today? The first one is communication. This is not something that was part of my training. I grew up in a different culture, in a different era, and you put your head down, got your grades, did the work, and you moved on. And you realize over time that particularly when you're doing research, and you're doing research that touches upon many different customers, stakeholders, that the communication matters. And simple examples like talking to the local Texas Department of Transportation. And we were speaking with them about the NSRS, the Spatial Reference System. And the conversations revealed quite clearly that the consequences of going to 3D in positional geodesy and allowing for time rates of change in that geodetic model, which we in our satellite geodesy profession took for granted. For us, all coordinates for x, y, z, and x dot, y dot, z dot were a natural part of the time evolution of coordinates. And in surveying and in surveying practice, in safety of life, civilian life um, applications, the transition to NSRS was, and things have been said about the transition to NSRS. People doing the NSRS have talked about this, the acclimatization. But it turns out that I had to be a good communicator on that also, and that in the sense of being able to talk to stakeholders, being able to talk to supporters in our communities who support our profession. And that support, I think, is very important if we are to retain the eminence and prominence of geodesy as a science among our community. It's no longer simply between us and the sponsor. And as I said, this was not a part of the instruction or training as we were becoming scientists. So I would say that that is something that we should very definitely give attention to. Technology drives a lot of what we do. It's, don't want to use the word siloed, but that has been the case, that someone else takes care of the technology and we utilize it, or we utilize the data. If we do the analysis, we don't care as much about technology. I think those lines are becoming blurred. They are less clear than they used to be. And particularly if we have to create some unconventional opportunities, I think it is necessary for us to, if you will, encroach upon other people's expertise. And so technology is one of those. That's one of my motivations of going into a physics lab and trying to, not literally, but going into the physics lab domain and understanding what is getting done and see how it can be brought out into the geodesy application. That does take some time commitment that a lot of us may find challenging. Life is busy enough as it is with the practice of geodesy. But I think it is super useful to be keeping track of technology and always thinking about how we can bring it. I think that is to the betterment of geodesy. And that frame of mind perhaps was not as common some years ago as it should be now. Physics and math principles, a part of me wants to say that there is probably not that much fundamental physics um, left to explore in geodesy, but that's probably wrong. It's a matter of finding the right thing. So it doesn't get as much uh, proportionate attention from among the number of investigators, but the math certainly does. And I'll come to those part of the math in a moment. Uh, Data science, and that definitely, so data science just happens to, I mean, the first data scientist was Kepler in my profession. And his obsession with the remaining 20 arc seconds in the measurements of the motion of Mars gave rise to Kepler's laws and to modern calculus and dynamics and matter of fact physics as we know it through Newton's work. And the data science is equally as important today as it was then. It's nothing strange to us as geodesists, but definitely its wrapping in the AI ML is new to the community. And I think what is true is that a large number of practitioners are doing this, but they perhaps don't have the forum that really highlights how geodesy could be driving the science of AI ML, or AI ML could be altering the science of geodesy. I think in our professional gatherings, we should make a little bit more time to specifically discuss these topics. Sessions do appear at EGU and AGU dedicated to data sciences and AI ML for geodesy, but that is something, it's a welcome new trend, let us say, and it needs to be accelerated. And computational science, I am keeping it slightly separate from data sciences because particularly given the larger data sets, the use of supercomputers is not as common as one might like it to be. Certainly, for example, in my discipline of flight, fluid mechanics and materials get to utilize the supercomputers much more than we do. But then our colleagues in modeling in the Earth system sciences, which has a very close relationship to geodesy, they certainly are major users of computational sciences. All right, so those are the building blocks in which we practice geodesy today. And the toolkit we have, the toolkit is stated from the viewpoint of an engineer, as you can guess. And the toolkit improves every day. So from my viewpoint, the toolkit includes some elements such as estimation, data assimilation. Those are methodologies, algorithms, and approaches to doing estimation, data assimilation, and uncertainty quantification. We utilize these certainly. Optimization, the inverse theories in regularization is common to the gravity field inversion. And optimization techniques go by leaps and bounds. Software engineering, so we can tackle the large data problems. And as I said, AI and ML, those are some of the basic toolkits. What I found interesting, so estimation I've always practiced. Uncertainty quantification is a language I have learned over the last decade. Optimization actually is sort of it comes and goes. When you want to work on the inverse theories, you go look at what they have done in other disciplines. And then every time I go back and see what has been done in other disciplines, it's kind of an impressive surprise how fast these fields have moved. In all of these, what is interesting to me from my personal experience is that in all of these fields, the developments are not being driven by geodesy. You may or may not agree with that observation, but what I find is that there is conversation about certain attributes of the problem. So for example, in the gravity field inversion, we went looking for, from first principles, my student and I, we arrived at the idea that we needed edge preservation in the gravity field inverse problem. Why do we need edge preservation? Because you see our current practice in mass estimation from GRACE is to introduce mass cons that have boundaries, mass concentrations that have boundaries at the land-ocean interface. Well, that is somewhat artificial because the gravity phenomenology does in fact smear across the land ocean in the physical principle, is a physical fact, smear across the land ocean boundary. And leakage has been studied in that problem for quite a while. But it turns out that the total variation regularization was actually designed for that purpose. But that was designed for that purpose in the case of image processing, not for gravity field inverse theories. Right. And so what happens? So why is it important that these developments in the other fields are not being driven by geodesy? What I find is that the problems, the solutions set up as motivated by other fields is not best suited to geodesy. Now, you can either call that a challenge or you can call that an opportunity, because if it is not best suited to geodesy, to make it work for geodesy is a good degree topic, right? And so that is nice. But on the other hand, that also means that the separation between applications, say, for example, in image processing or in video games and so on, is not is equally applicable for us in geodesy. So I think that is one of the uh, important things to keep in mind, and particularly these large-scale computational techniques are advancing in a lot of disciplines. They're being motivated by a lot of disciplines. And there is much to be learned there. And this is something that we must all be very mindful of looking around at who's saying what in the other fields. And I don't know what are the preconditions for geodesy to drive one of these disciplines. I don't know if that will happen. A part of me thinks there simply are not enough of us geodesists to drive it. But you don't need the numbers of practicing geodesists to drive innovation in the field. You just need an important enough problem. So I don't know where the answer will come out on that one. All right. So a couple of examples. One of them connected with the Earth's gravity field. That's pretty much what I practice. So we have essentially from measurements from space, we have two options. We can observe the motion of a point. That point typically is the center of mass of the spacecraft, which is in free fall. And we can observe the motion of that point relative to the Earth. We can either observe it directly from the Earth using observatories on the ground, or we can observe it relative to satellites such as the GNSS or the GPS or the Galileo constellations. The other option is to look at the tidal potential or the differential or the variational potential or the force field in the close vicinity of the satellite relative to the center of mass. And that's the principle behind gradiometry. So I just want to put this up as the two basic methods by which today by the way, space missions have flown measuring both of these. One on the left, there's a long multi-decade history of tracking satellites. And in fact, the first results on the pear-shaped of the planet were obtained about a year after the launch of the first artificial satellite. So the technique on the left is as old as the space age. And on the right, state of the art has been the flight of the ESA Goche mission that measured the gravity gradients. So both have been done and meaningful results have been derived from both techniques. I just wanted to put this up for as a conversation lead in. What do we have? We have on the far left, we have the technology. Quantum sensing is coming along. Fundamentally, the sensing of gravity is based on time and frequency metrology. And then you take those and you develop space systems architectures using simulations and computing methods. And so in order to, there's no reason why a geodesist should not develop the space systems architecture. We understand the end use of the scientific data products and the methodologies by which we extract the gravity field. So that same methodology can be used to architect the space missions. And we use computational method simulations to develop the architecture. And the shaded box are shaded because developments in that is in the domain of the physicist. And this sort of is an example of a bridge between geodesists, looking at the Earth system science on one side and looking at the technological innovation on the left side. In between, so these are some of the popular techniques. Satellite laser ranging has been around forever. Satellite gravity gradiometry in green, and tracking of satellites either between two low orbiting satellites or between low orbiting satellites and the high orbiting satellites. These are some of the techniques, all of which have had space missions flown. All right. So right now, this problem is a problem of parts per billion. This is one of my favorite sequence of figures. A little bit of, yeah, I like this topic, so I'll just walk you through this. You already know all of this. 9.8 meters per second square standard gravity, variations of the order of millimeters per second square in going from the equator to the pole due to the bulge. Once you remove all of that, you begin to see features in the gravity that reflect the long-term crustal tectonic structure of the planet. This is in the fourth or the fifth decimal place of the G, and 100 microgal is a millimeters per second square. So I would say that's part per 10,000 of the G. And this color scale showing the permanent tectonic features are parts per 10,000. And then you zoom in some more. These right side diagrams show the root mean square gravity variations on the order 1,000 smaller than that. These are parts per million, therefore. And you're looking at ocean tides on the top right, and you're looking at the weather both over land and over the ocean on the bottom right. We do know a lot about these, by the way, right? We have been studying the planet for centuries. There have been a lot of other measurement techniques that have given us information about modeling techniques that have given us information about tides and about the atmospheric variability. And so these are in the parts per million. Once you cut across all of that, what is left over in the units of microgal now, or the nano G, is parts per billion variations. And this is the topic on which approximately a paper a day has been written over the last 20 some years. I think we're up to about 7,000 publications utilizing GRACE data and addressing pretty much all domains of the planet. And all of these variations are of the nano G, right? Parts per billion. And that actually, in a way, gets underestimated in two ways. And that actually has impact on education, training, and on research. So what I'm saying with this diagram is that the existing knowledge base before GRACE and existing numerical methods, existing algorithmics were adequate to explain the GRACE measurements to within some parts per million. And what innovations we made using GRACE data were on the order of parts per billion. Now, everyone publishing papers today is pursuing ever smaller signals, but I think it is worth pausing and noting that these are at the parts per billion, because explaining those parts per million that are actually already embedded in our software, teaching these parts per million that are embedded in our software, that is not easy. That does require time. It does require an innovative curriculum for those of you that are instructors. And it requires us to have a breadth of expertise. Most of us are used to teaching a single topic, right? Flight mechanics, linear algebra, controls. But when you look at, I'm just speaking engineering topics, but if you look at the totality of what goes into what is in the background before you even arrive at the science that lets you address hydrological or ice sheet variations, that is a lot. It's a lot for instructors to squeeze into courses. It's a lot for a student to understand, because the student's dissertation is going to get written on the parts per billion. And so I think we need to find some ways to speed up or make that instruction more efficient. There are some thoughts. Uh, the word YouTube gets used a lot, but it's not clear if YouTube, I think, doesn't help if you don't have the right topic to make a YouTube video on. And it's not clear we have sat down and said, what are the building blocks of education? What are the building blocks of research that allows the student of the next generation to focus on to what is new in this diagram and this movie clip that is moving on the screen at the moment? That's worth a conversation, I think, in building those pieces of instruction. And it's not just instruction in the topics, it is also what the intelligence community calls tradecraft. Right? There are some choices the analyst must make before you extract these observations. What are those choices? And training that, the methodology of training that in a fashion that actually appeals to the modern student is a challenge today. And we have some activities going on that. It was an interesting anecdote. As I said, I have a 30-page presentation on Earth orientation for upper division undergraduates. And I put that presentation into Notebook LLM and asked it to summarize it. And it presented about a 40-minute narration, a podcast. It is interesting. The podcast completely missed the significance of images inside the presentation. The past podcast did, in fact, identify some core building block pieces of knowledge, like the analogy of the Earth orientation to the spinning top problem from mechanics. It actually identified that, and that is pretty impressive. And so what my hope is to actually then conjoin it with a couple of other topics, hopefully with the help of Notebook LLM again, and help it get AI to help me identify some building block topics that are common to the geodetic enterprise, right? Earth orientation, dynamics, they're all the building block topics. And if I can get them to identify some basic topics in mechanics, in coordinate geometry, things like that, I think that will help accelerate the training and education on the path to where a student can then start, or the next generation researcher can get faster to the point. Mine was a painful path to this, by the way. It's just the old tedious way of doing things. So it's worth exploring if there's a faster way, if we can use AI to help us get there faster. All right, so the other challenge on the scientific side is that how do you improve on a parts per billion problem? Like every last bit becomes a little more difficult. This is the diagram I've shown before. For those of you who have seen my presentation, x-axis is the length scale, y-axis is a metric for the quality of the mass change estimation in units of water height. Each dot, each cross, if you can see them, is a basin of interest, either a hydrological or a glaciological feature, and it gives you a sense for the signals that have been currently seen using GRACE follow-on MASCON solutions by various authors at different length scales. Right? And some of these have been identified just for visual reference with those vertical annotations. Those open symbols and the solid symbols are the desirements or the goals that are articulated in the Earth Science Decadal Survey. And the solid lines indicate what is accessible to different kinds of space missions. And the further right you go, the harder it gets to pull down these techniques by an order of magnitude. That simply follows from the problem of upward and downward continuation and the attenuation of the high frequency features of the gravitational field as you go further in height, right? And so closing that distance between the lines at about, say, the 100-kilometer resolution and getting down to where the solid symbols are, That is a challenge that is considerably harder than whatever we have accomplished before. It's a technological challenge, as in the instrumentation development. It's a mission architecture problem, as in the heights that you follow. And it is a challenge in picking up which technique is the best option. And compounding all of that, it's going to be a money problem because stuff inevitably always gets more expensive. Right? And so that's actually a real challenge in the sense of a new accomplishment for the next generation would be to ask, how can we get this down? It doesn't have to be, by the way, satellite methods. It could be other methods. This is a nice illustration. Parts per billion is nice, but then beating down on that is pretty hard. And that's something to remember. And the same thing is actually true in any discipline. We talk about millimeter precision positioning from GNSS for GNSS, well-monumented GNSS receivers, right? And yet, if you look at the volume of publications, there are some very difficult topics awaiting us if we are to attack that millimeter and take it to the sub-millimeter in GNSS position. Another example, that of reference frames, and this is this is a different nature of a challenge compared to the gravity field. The gravity field is in the nature of techniques and technologies. This is actually in a shifting use case. What do I mean by that? So we have in West Texas a McDonald Observatory since 1939. That's been an astronomical observatory. And if this is still a laser pointer, this little dome here that you see, this is the Hobby Eberly telescope. It's looking at dark matter exploration. And this shelter here is intended to contain a satellite laser ranging system eventually. This is an astronomical telescope, again at McDonald Observatory, that in 1969 through the mid 70s was used to range to the moon in support of the Apollo program. Right? And then that evolved into the McDonald laser ranging system, which is on the right side here, which is now defunct. It's basically been disassembled, got hit by lightning, and et cetera, et cetera. Up on the right is actually the VLBI, the Vigos dish, which is now operational. So this is NASA and UT collaboration. The systems are from NASA, and UT prepared the infrastructure. And this entire infrastructure is scoped to meet the needs or the challenges presented by the sea level problem. And in fact, if you look at the methodologies that we use, if you look at the requirements to which the community works on the reference frames, they are the toughest requirements are the sea level requirements. And whether we realize it or not, over time, our habits have transitioned to solve the sea level problem. Our habits in reference frames and positioning have transitioned to solve the sea level problem. And that includes everything from scoping the hardware to the algorithmics that we use. What happens then? Now, position, navigation, and timing comes along. PNT has always been there. It has had national and international attention. It's not like we just discovered PNT. It has always been important, right? And so, but the new thing is that there is an interest in PNT reaching all the way out to the moon. The near Earth PNT remains important, but then the distances over which PNT becomes important stretches out now to the moon. And it's not an exaggeration. The lunar and terrestrial geodesy will need to be integrated. Right? And so there is the hardware problem. What devices will we use? Well, when that's really up to the stakeholders to solve in a way. That's what I'm saying there with the first bullet. So likely or will have to get solved by the stakeholders. You and I as investigators might make breakthrough in specific technologies, but the infrastructure is beyond our academic reach. And the stakeholders will have to put that into place. However, we can, in fact, inform the stakeholders on what that infrastructure should be. And that is happening. If you see, there are plenty of working groups. One is called Logic at Johns Hopkins, and then there is NASA has several working groups looking at how to respond to the White House's directive on the lunar coordinate time, and IAG has a working group on this, and ESA has activities reaching out in this direction. So yeah, it is of relevance to us geodesists. And the challenge here is a research transition. How do you take about 30 years of habits, what we do with parameterization of the observation, how we combine the different techniques and so on, are conditioned on targeting the sea level science. And then now, which of those habits should we change as we serve PNT out to the moon? The few things I realized, one of them is that in that scale, in the Earth Moon scale, the orbiting assets become dominant, and orbital techniques therefore become dominant. There were not that many groups. There was Goddard, there was us, there was JPL that actually had instructional capabilities in the use of satellite orbits for reference frames. And some of those things have fallen off the curricula, and they will need to be brought back in. Not only will, so all of those older techniques, which are basically developed and refined in the Topex era, because Topex was one of the first, well, it was the first in my experience, where there are papers on how order one harmonics, errors in order one harmonics manifest themselves as a Z shift in the frame, or geographically correlated orbit errors influence the orbit and the realization of the reference frame, or the geocenter, or the network distribution. All of those problems were solved when the tool was low Earth orbiting satellite. Now you go out to the moon, all your orbits are cislunar, and they do not look anything like um, Keplerian orbits or perturbed Keplerian orbits. They are a completely different beast. And a reference frame estimation based on those beasts, I don't think there is that much of knowledge base. How will you build that knowledge base? We built the knowledge base in the Topex era using data. We don't have that much data in the cislunar space. So this is actually something where an application is transitioning a field that are reference frames, and it is going to transition the technology, alter the technology. It's going to alter the algorithms and methods we use. And therefore, it also has to alter what we teach in the classroom to serve these topics. Call that an opportunity, right? Because it has to be done, and we can do it. So that becomes an opportunity. All right. So in summary, any discipline, not just geodesy, grows ever less isolated. And saw an example of how it is altered by changing applications emphasis, like in the reference frame, or the technology and the methodologies because of the pursuit of the greater resolution and accuracy in the case of the gravity field. Because those pretty much, I mean, responding to those is inevitable because that's what controls how the research resources are prioritized. Each discipline is altered by advances in other disciplines, and there are plenty of opportunities for that, particularly as everyone grows more data oriented. And it's also altered by changing cultural conditions. I have to learn how to talk to the younger student applicants, and I cannot expect them to walk in learning to speak my old-fashioned language. And so recruiting students is a very different game even now than it used to be 10 years ago. And attracting them, there are interestingly students that are attracted by discovery, and there are students that are attracted by service. It is possible to encourage students to join a field just for the prospect of serving society, for example. Ideas like national security do appeal to some students. And so that is something that we should acknowledge and respond to as we learn to talk to the students. Of course, the challenge always is opportunities. It's always easy in hindsight, this thing. The harder thing is to figure out which trend to follow as in which trend to chase down to see what value it might offer. And the best is, of course, you create your own trend because you have a problem that needs to be solved. That's cool. That was nice. But I found usually in my 35 years, I don't get too many opportunities to start new trends. And most often it is actually necessary to keep track of what the others are saying because in the end, all science is collaborative. All right, so I'll stop there and be happy to answer any questions.
Great. Well, thank you so much. I'm going to open up the chat here and allow folks to unmute themselves and turn on their video. So hopefully everyone can raise their hand or just unmute themselves if they have a question they would like to ask. Just see if this is actually working.
Oh, I can hear you.
You can hear me, but
Oh, yeah.
I'm the host, so I'm controlling the microphone.
Yeah.
But let's see if anybody else have a question they would like to ask. I'm just admitting somebody into the room here. Um, if not, I guess I'll just start with a question. Oh, let's see. We have just a comment. Thanks for sharing your insights. You were sort of ending on the question about careers and thinking about um, you had some good suggestions about that, but I was wondering if um, you wanted to expand upon those a little bit, just to talk about all the different challenges you talked about, all the different technologies development. What do you see as for, in terms of helping to recruit students? You mentioned a couple of options in national security and discoveries, but you want to elaborate a little bit on what if sort of a sales pitch we make to help recruit students to come to Geodesy and work on these types of problems.
Yes, we've had to learn that a lot very quickly. Actually, I will say this. Um, Students will track trends. That's undeniable. That's one part of it. Second is the uh, y- your particular research problem doesn't have to match the sexiest problem of the day, but you can make the case that working on the problem that I'm working on will prepare you to tackle the hard problem. One of the things that you have to tell the students, I have to tell the students, is don't get obsessed about which topic you're working on. They all want to know what project will I be working on. I tell, does that really matter? It doesn't actually. It's the process that you need to learn how to break down a problem, how to solve a problem, how to ask the questions. And you can take those skills to any field you want to. Right? I think that generality does appeal to people that they are being prepared to be versatile. And I think that's very important because I will say that I can train 10 people, 6 of them will not enter Geodesy. They will take their data science skills, their analysis skills, and their engineering evaluation skills, and they will go find the best job that gives them the biggest amount of money. And you cannot blame them for that. And so we chug along, we just keep training them in the right way to be flexible. At least that's my philosophy. And those then that do join GRC will be valuable members of the community. And that is the victory we can take with us. I don't know if that answered your question.
And I think that's good. I
Yeah,
think it's
yeah,
it's a good answer of um, helping people focus on the skills they're developing and the skills, not just technical skills, but as you say, problem solving skills,
yeah,
critical
yeah,
thinking skills,
yeah.
is a toolkit that's widely applicable in Geodesy and beyond.
Yeah, and the students do, in fact, they see today, for example, my students do see that there is opportunity for leadership in the field. This has been said that people have the geodesy workforce is aging, and the students see that, and there are students who see the opportunity for being leaders in the field, and they do gravitate towards. Not everyone does. You just need a few, though. So. There is a question on
In the
NISAR.
chat, yeah, from Luciana was just
Uh,
asking about what do you think will be the challenge on processing data from NISAR once it's launched, hopefully in June, to drive science discoveries.
okay, so I will answer the question according to what I've heard from my colleagues, right? Which is that one of the hardest things is to prepare data in a way that actually you have confidence in its use right off the box. And that is being talked about as a challenge to 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 uh, to prepare the data in such a way that anyone with some nominal training can walk in and start utilizing it. That's a very difficult task. We have done that, attempted to do that for Grace and Grace follow on. So I understand the complexity of it. But the complexity of the mission and the complexity of the instrument suggests that that will require a lot of attention. Uh, and that will be a challenge. And on the science side, I'm sure there are analysis challenges, but it's beyond my expertise to enumerate those. You are muted, Luciana, if you're saying something.
I'm just saying thank you.
Okay. And Kevin, so I think my words did not quite come out right. Um, what I was saying was that behind every discipline, there is a physics, right? And much of the physics behind the science of geodesy. I'm not saying we understand everything that moves the position of a receiver. There much remains to be done, right? But the science of geodesy itself, it's not clear to me if okay, let me say it in the right way. I don't want to say it in the wrong way. If we had 100 geodesists, not many of us are working on the fundamental science of geodesy, as opposed to many more of us are working on the utilization, interpretation, and techniques of geodesy, if that makes sense.
This is Dave Zokoski. Can you hear me?
Yes, I can.
Yeah.
Yeah, I was intrigued and I appreciate Kevin's comment because I was thinking along the same way. But you made a very in the beginning you said the need of importance enough. You need an important enough problem to engage the geodesy community, which I agree. But in history, before, and I worked for the National Geodetic Survey for 35 years, but um, NGS had two major projects that they were working on, the readjustments and the reference frames and so forth. Back in the 70s, they started it. And they were sending people back to school. And so, and I was one of the benefited from that. But at the same time, there were a lot of people there. Well, Dick Rapp was very important with the gravity and so forth. And there were a lot of military people. I mean, all my friends came, and a lot of people came from around the world to learn about geodesy. Because you're right, it was in the issue like with Dick Rapp and so forth, it's getting better gravity, improving it, and using the tools you had. And boy, there's a lot, as you talked about, a whole lot that's come through since that time, which is pretty amazing. So, and I keep pushing geodesy and the importance of geodesy crisis, working with Mike Beavis on this, but I get people pushback saying, "Well, we solved all of the problems in geodesy. We don't have any other problems."
Yeah.
And geodesy being the foundation for every positioning thing you do, there are things, and it's kind of hard to talk back to them because it's like you need someone that's just gonna think through his imagination, think of something and say, "Oh, hey, I just thought about this. Well, let me see if that fits." That's not something you. That's just not something you say is going to happen.
No, you
It
have,
just
yeah, it
happens.
happens. It just happens. I completely agree with you. And so you have to create that conversation to where geodesy remains a topic of conversation often and with some vigor, right? And so what drives, why would there be a conversation and why would there be that vigor? And there are actually, uh, you can tell, I live in Texas,
Yeah.
and the Army Corps is spending a lot of money in the along with the state, and this money ranges in the billions, by the way, on flood control projects,
Yep.
and that has been a major need to have the right heights. I was told there is some 7 or 8 digit number of cost for every foot they're wrong on the berms, right? The construction cost is just insane.
Yeah.
Uh, Bridge between that and kind of the global geodesy that we practice in academia, right? If we bring in those everyday concerns to the population into the conversation in the same forum, right?
Yeah.
I think a student will, I know for a fact, student will be interested very much in contributing to having the right height to the berms and to being part
Uh,
of geodesy. And so that driver to make the connection, and look, state, this is just a regional example. I'm sure everybody can
mm,
find examples. State is spending $6 billion on flood control measures, and it cannot do it without geodesists. That is a
right.
fairly powerful argument. And so that keeps the conversation going. And then organically, someone somewhere, their mind will wander to the more fundamental aspects. And you know, once you start off on a problem, the mind goes where it goes, and it should
Yeah.
be allowed to go where it goes. I think those are good opportunities to create
And
connections to create. Yeah,
yeah, and I agree with you. I've been talking about it for a long time,
yeah,
and I did a lot of work in New Orleans area about with subsidence and
yeah,
floods and so
yeah,
forth. So I agree with you. And trying to develop better heights is something that I've most of my career in the government was dealing with getting better heights. And right now, I keep trying to get with other government agencies as well as industry. Because to me, the automobile industry really should be reaching out to try to get geodesists and others to on board to be able to integrate the positioning and not just GNSS, but you got LiDAR and you got other
yes,
tools
local
that
sensors.
cameras. How do you integrate all that? But for the life of me, I can't get anybody bite. But industry is always the bottom line's money. So that's hard. It's very
But
hard to convince them.
money also makes academia go around, not just the world.
Well, yeah,
That's the
definitely.
reality of it. Yeah. So,
Yeah.
Kevin, there is a second part to your question that I did not answer. I think it's a little bit beyond me. I'll have to think of it a little more carefully as to what we are doing in geodesy, how it would alter physics, fundamental physics. So I will need to think more closely about that.
And that's why we need more geodesists. We need more people thinking about those and just just bringing it all together.
Yeah.
And the time, like using clocks to measure heights, there needs a lot of they need more work in that. Although clocks to do that are very expensive, but if you till you develop it, then it will become cheaper once you can develop it and you can find a
Yeah.
use for it. I remember um, years ago, Arnie Berheimer came to NGS and he talked about clocks and everything. This is
Yeah.
back in the
Yeah.
1980s, early 90s, because I was the NAVD project manager. And he talked about all this, obviously not ready at the time, but it's coming. So
Yeah. Well, it's
that's why
here.
we need to,
And in fact, if there is a second word beyond AI and ML that will attract new students, it's the word quantum.
yeah.
And the folks at NIST had a nice blog that said, if you work with lasers, it's quantum. Just call it quantum. It is quantum. Nobody can protest it. And quantum is a hot word now. It's important. And so is AI ML. And if you say, hey, look, AI ML and quantum all together, actually, that works out in the context of quantum gravity gradiometry also. So those connections are there to be made. And one of the things I think space flight is also another way, just the idea of space flight 60 years after the first launch, or 70 years after the first one, it still holds attraction to get people in. And use anything we can to get students in, right?
Great.
Most of the things that you have been mentioning are not typically associated in most people's minds with geodesy. Space flight, space science, things like that are, people don't connect the word geodesy to those things. So Dave's point about not being able to get bites on people to engage in geodesy, there's a blur in the way I see it right now. There's a big blur between geodesy and geophysics. Geodesists and geophysics are almost identical. These, no, not quite, but they're very much blended. And so the real push, or the real aha moment for people understanding about geodesy is how it serves society. Can I drive my car and make sure it doesn't hit another car while I'm sleeping? Things of that nature, and other things that serve society. It's harder to, in my opinion, to engage new students in geodesy when they can say, well, I'll just skip my geodesy. I'm going to go geophysics and I'll get a little bit of geodesy, what I need. There's a blur in that area right now. The geodesy is not so distinct and so unique and so understood that it's very clear to young people what it is and why I should go there.
There is a perspective of geodesy from geosciences, and there is a perspective of geodesy from engineering. And I think it may be worthwhile spending some time in, I won't use the word reconciling, but in looking at those two side by side and seeing where are they different, where are they common, and how can I steal some from you, the good stuff, to make it attractive to engineering students, and how can you take some of mine to make it attractive to the geoscience students. I think that is a good exercise. This came up, I was at a workshop where Jeff Freimuller was presenting a few minutes on the state of geodesy education and where the university stood on it. And so I looked at his content and I said, if an engineer had written it, it's worthwhile redrawing your presentation with an engineer's hand to see what it looks like. And you would get a little bit different perspective on geodesy. And I think the union set of the two is going to become essential, particularly to the extent we are driven by the numerical methods and by the technology, because technology is becoming so dominant in this that technology has always been dominant. So let's be clear about that. But it remains dominant, and the numerical methods are so prominent in geodesy that union set between the geosciences view and the engineering view is worth developing, put it that way.
All right. I see. John, did you have something you wanted to? Nope. No, you're just turn on your video to say hi. Good to see you. But Luciana has her hand up, so go ahead, Luciana.
Yeah, I just have it's out of curiosity, okay? Like I'm in seismology mostly, okay? So in seismology, we have all these seismic arrays that we basically stack up so that we get better resolution. And in one of your slides, you made the case from going from, I don't know, kilometers to meters to millimeters and submillimeters, okay? Is there any push in geodesy to have like a race of GPS or gravimeters or something like that to increase resolution, to make that jump? Because that would be both an instrumentation, but also a technological advance. But I think the important part is like, why do we want to go there? Okay, because I mean, I think even like 20 years ago, people were wondering, why should we sample more than once every hour a GPS, or more than once every minute, And from there it went to like
real time. Yes, yes. Yeah. So the best analog of your seismic experience is to cite a initiative called MAGIC between ESA and NASA. Just staying with my satellite gravity example, where a constellation of gravity missions is imagined. And the constellation, the fundamental purpose the constellation serves is to improve the anisotropy. A single satellite mission is an anisotropic sampling of the gravity field. To make it is good to have it isotropic just from the viewpoint of observation and invertibility. And the second pair makes it more isotropic than having only one pair. And there is one
Having
part.
two components or something. in
Yes,
technology.
yeah.
Okay.
And since the satellites are continuously observing the planet, you do get the global sampling. But if you have more than one satellite pair, there are people studying 6 satellite pairs of GRACE-like missions, as practical or impractical as that might be. But for the specific purpose of improving the redundancy, the trying to get closer to what used to be called the synoptic view of the planet, right? And so those are the ones I know of, which are analogous to using arrays of seismometers. Expensive options. So
Well, it is, but I mean, but if there's a very good case, even
case,
an
then yes, the
economic
investment
case
could
to be
be.
made.
Yeah.
I mean,
Yeah.
it's not out of the question.
Yeah. And
Okay.
on the science side, most of that need, the argumentation for that is driven by the study of the water cycle, water availability at the few days, variation of water availability at the time scales of few days are the key motivation for presenting those.
Well, thank you so much. I enjoy your talk very much.
Thank
Yeah,
you. I
thank-
hope that was useful. So
Yeah, so we are at the hour, and I guess we will thank you again for a very great talk, great discussion after the talk. Appreciate everyone being here, and we have a recording that we will make available on YouTube, hopefully within the next couple of days. So
thank you. I appreciate very much the opportunity.
great. No, it was a great talk. We really appreciate your perspective. Thanks again,
Thank you.
everybody. We'll see you soon.
Bye-bye.